Hi, my name is Kennedy Rand, and this is my Lab 1 video report on charged tapes. The purpose of this lab was to give us initial exposure to charged objects and how they interact with our surroundings, and to learn to approximate their amount of charge. The experiment involves modeling the tapes as point charges, then calculating their electric fields when interacting with each other from a small distance. The result was found that the positively charged tapes have a charge of about 9.7 times 10 to the negative ninth coulombs, which is equivalent to a deficiency of around 6 times 10 to the 10th electrons. The preparation and methodology of this experiment is as follows. First, I had to create multiple charge tapes. This procedure is represented in the top right. After creating two charge tapes, one of the tapes was set up to be hanging, while the other tape was held below to cause the top tape to float in equilibrium. This is depicted in the diagram to the bottom right. This model gave me the tools to make several important calculations involving the tape's charge. To achieve the goals of this experiment, I used several fundamental principles of physics. First, I used the law of attraction to determine the sign of the tape's charge. I also used Newton's second law, which states that an object in equilibrium has a net force of 0, to set up an equation for the electric field. Finally, I was able to use Coulomb's law to derive an equation to calculate the charge of the tape. Before continuing, we must note that several assumptions were made in this experiment. First, we had to assume that each charged tape had the same amount of charge. We also had to treat each tape as a point charge, with all of the charge concentrated at the center of the tape. Now that we have established the basics, we can begin looking into the results of the experiment. The beginning of the experiment involved testing how the charged tapes interact with their environment. Initially, I expected two charged tapes to repel each other. This proved to be true, as tapes have the same charge and like charges repel. I also initially expected a charged tape to have no interaction with neutral objects. This was not the case, as we now know that the tape was attracted to neutral objects due to their polarization. Next, I was able to determine the sign of the tape's charge by holding it up to a negatively charged pen. Because the tape was attracted to the negative pen, we can determine that the tape is positively charged. After determining the sign of the tape's charge, I was able to set up the model, as seen again in the top diagram, and determine some of the key values. I first calculated the mass of the tape in kilograms, and then measured the distance between the floating tapes in meters. Because the floating tape is motionless, I determined that it is in equilibrium. Thus, the sum of the forces acting on the tape, in this case a gravitational force and an electric force, is equal to 0. This is depicted in the free body diagram on the bottom right. The gravitational force is then calculated using mass times gravity and equals around negative 0.002 newtons. At this point, we know that the electric force acting on tape B is equal and opposite to the force of gravity, and we will be able to use this value going forward. Next, we know the calculation for electric force of a point charge through Coulomb's law and can solve this equation for Q to calculate the charge. Plugging in our known values gives a charge of about 9.7 times 10 to the negative ninth coulombs. I then calculated the number of deficient electrons by dividing the charge of the tape by the charge of one electron. This calculation tells us that the tape has a deficiency of around 6 times 10 to the 10th electrons. Lastly, we can calculate the ratio of deficient electrons to atoms on the tape. This was done by first calculating the number of atoms on the tape. Next, I divided the number of deficient electrons by the number of atoms. This calculation gave a ratio of around 28, representing the fact that the tape lost about 28 electrons for every atom. After concluding the lab, I was able to create a visual representation of the system through my GlowScript code. Tape B is represented by the blue particle and is hovering over tape A, the red particle. The red arrow represents the electric force acting on tape B, and the orange arrow represents the gravitational force acting on tape B. The values I calculated previously are calculated correctly in the program and included in the output. I chose to also include a blue arrow representing the electric force acting on tape A as well, as we know that this force is equal and opposite to the electric force on tape B due to Newton's third law. You can see that the arrows are all equal in size. This is consistent with my calculations and helps to reinforce that this model is accurate. Lastly, we can consider what would happen to this model if the charges of protons and electrons were flipped. To become positively charged, our charged tape gave up negative electrons to the base tape. Thus, if electrons had a positive charge, we would expect the tape to have an overall negative charge. We would therefore expect the tapes to be repelled from the negatively charged pen. However, the interactions between tapes and between neutral objects should remain the same. And finally, we must acknowledge a limitation of the lab. Touching the tapes allows for the tapes to disperse their charge and become neutral. I worked to handle the tapes as minimally as possible throughout the lab. However, touching the tapes was unavoidable. Thus, we can recognize that in an ideal scenario, the tapes would not be handled at all, and this might represent a flaw in the lab's data. Thank you for watching.